Okay, Algebra 2 kids, I'm home with a sick kiddo today. You might hear him in the background. This is Kason back over here. So if he pops in from time to time, that's who that is. But I'm going to record this lesson and give you guys time to work in class on your homework assignment, hopefully. And I should be back tomorrow. Assignment for this section, page 100, it's written up here at the top. And this is kind of a short, easy, I think, section. It's talking about linearity, so it's talking about whether a function is linear or not. Okay, that's like one question that we're asking. And then symmetry, and there's two types of symmetry. There's a line symmetry. And we'll talk about each of these below. Line symmetry and something called point or rotational symmetry. Okay, so not too many concepts today, just kind of going through the motions here. So a linear equation, we've talked about linear equations before, and they usually look like y equals mx plus b. You know, and those will have numbers in there. So like y equals 1/2 x minus 6. That's a linear function. But we've also found that it doesn't have to be written in y equals mx plus b to be linear, right? Like sometimes we'll have like -3y plus 2x equals 5, you know, and then we would have to solve for y. So that's a linear function too. It's just not in the slope-intercept form like we're used to seeing. Also, we've seen things like just y equals 4 or x equals -3. Those are all linear functions. Those are just straight horizontal lines or straight vertical lines. And those are still linear functions, okay? So what we're really looking for in a linear function is like usually it will have an x and a y variable, and they'll be to the first power, okay? Not like y equals x squared, that's not what we want, or y equals x to the third, we want y equals x, something like that. But keep in mind, it doesn't have to have both variables. It could only have a y or only have an x, but we don't have like weird things going on. Like here's some examples versus non-examples, and instead of using y, they used f of x, okay? So just keep in mind that that's the same thing, but this is y equals -2/3 x plus or minus 1. This is linear function, check. Okay, y equals 1/2 x. There it would be like +0, but that's still a linear function, check. This one is not in slope-intercept form. We have the y is here, and normally we would solve for that, but that's still a linear function, so check. Okay. Here are non-examples. We'll talk about the reason why things are going bad here. We don't want x in the denominator. No variables in the denominator. You can have fractions like -5/8, right? That's okay, but as long as you don't have a variable in the denominator, okay? This second one, look at him and see why he's not. We can see that we have y squared in there, so no variables squared, and I guess squared or cubed, you could say also, because it could be to the third power, to the fourth power. We don't want any of that happening. And then this last one, we have an x and a y that are being multiplied together. So this is bad. Two variables multiplied, not good. I can't write multiplied. I think that's how you spell multiply. Anyway, so we don't want two variables that are multiplied together. So things like that are considered non-examples. Those are not linear functions. Later on in this chapter, we'll identify like what those would look like. But for the most part, like these are not going to look like lines when we graph them. They're not going to look like linear functions. These all will, okay? So let's go down here. We have an A, B, C, and we're going to identify whether it's a linear function, yes or no, and then kind of explain. And here's my explanation, okay? When you're going through and you're explaining, we're going to just circle the part that's bad. On the homework assignment, if they say explain, just kind of give me this explanation over here. You know, kind of what we don't want to have happen. Or you can just say, like, this is the part that's bad. Okay, so we'll go through that. A, 3x plus 2y equals 8. That is not in slope-intercept form, but it is linear. So, yes, linear. You can just put yes, but I'm going to put yes linear. Okay, yes, it's linear. So nothing bad is occurring with that. B, f of x, which is just a fancy way of saying y equals 2 over x, but we don't want variables in the denominator, so not linear. Okay, and I would just point to that and say the x is bad, but for an explanation, we would say no variables in the denominator. And I'm kind of abbreviating, so if you want to do that as well. So no variables in the denominator, that's what is the bad part, okay? Part C, y equals 3xy minus 4. We don't want to have two variables multiplied together, so not linear as well. Okay, and this is the part that's bad, so no variables multiplied. That's the bad part, okay? We don't want that to happen, all right? So hopefully we're kind of a little bit better at identifying linear functions and what's linear and what's not linear, okay? We'll talk about later on like what these guys would actually look like when we graph them later on in the chapter, okay? But for right now, we're just going to deal with linear versus not linear, okay? Example 2 says the graph shows one function model of how the population of northern snakehead fish in a lake is predicted to change over time. So they're talking about time here and then the population. So the population is increasing from the graph is what it looks like, okay? They're saying the table shows a second function model, okay? So now they're doing something different and they're still doing time, still doing time and still doing population, but now we're looking at those and saying, okay, is one of these linear or both of them linear, right? So looking at just like this model A over here, we're looking to see if he's a straight line, and it kind of looks like a straight line, but I have the luxury of doing this. Let's do this. If I were to connect just those first 2 points and make a straight line from them, like I'm trying to make sure I go through this point and this point. If I continue that, this is what my straight line would look like. So we can kind of see that he like veers off this way a little bit, which is more like an exponential function, if you know what that is. We'll talk about those later as well. But this is not going to be really linear, okay? It looks like it starts out to be linear, but I would say, nope, it doesn't continue to be linear, not linear. Because it's not truly a complete straight line, not linear, okay? Now let's look at model B, and then when we look at this and we look at the table, we've done this before actually. When we look at this and we look at the table, we're trying to see whether the values are going up by a constant amount each time, right? Like if I am trying to find slope, I'm doing like y2 minus y1 over x2 minus x1, right? Okay, and we've done this before where we take this one minus this one minus this one, etc., right? Okay, but I'm not interested really in finding the slope at all. What I'm more interested in is like, is it linear or not? So let's just take, and we always kind of want to pay attention to the x variable. These are the x's, the times, and make sure to start with that they're going up by a constant number. So they are going up by ones each time, so we are good to go. Like we don't have to worry about that. But then the y's, we look at each one of those and we subtract them. So like 125 minus 100 would be 25, like we're adding 25, okay? 150 minus 25 is 25, 175 minus 150 is 25, 200 minus 75 is 25, so it doesn't matter. All of these numbers are exactly the same. And the fact that they're exactly the same tells me that this is yes linear, okay? Now, if we wanted to go one further, we can look and see, like, they're going up by 25s in the amount of time that this is going up by ones. So my slope would literally be 25 over 1 or just 25, if that makes any sense at all. Like we've kind of done the y2 minus y1 when we did this here, and we did the x2 minus x1 when we did that there. So 25 over 1, my slope would be 25. It's 25 all the way across the board, so yes, it's linear, okay? All right, now let's go into symmetry. Sorry, we've got toys all over the place. Kaysen's running a fever, but he's actually feeling pretty good right now, so he's kind of crazy. So anyway, all right. The graph of a function has line symmetry if you can draw a line through it and it's like reflected across that line, okay? So if it can be reflected across a vertical line so that its reflection maps exactly onto itself, and this is called a line of symmetry, okay? You guys might have done like a project in elementary art where you take a piece of paper and you fold it in half, and then you'll unfold it and you'll paint on one side, and then you'll fold it in half again and unfold it, and the paint will transfer onto the other side so that you'll have the same paint color on both sides. And that's like creating a line of symmetry, okay? So example 3, state whether the graph of the function has a line symmetry. If so, identify the line of symmetry. So we're looking at this parabola and we're saying, can I draw a vertical line straight up and down that goes through this parabola so that it's the same on both sides, or it maps onto itself? And sure I can. This guy right here, I can draw him there, and we see that this half is the same as this half, like he maps onto himself. So that works, and that green line is my line of symmetry. So we would say, state whether he has a line of symmetry. Yes, he does. And that line, the name of that line, we've named vertical lines before like that. It's going through the x-axis at 3, so the line of symmetry is x equals 3. Okay, Zen. Okay, sorry, you're going to get tired of that song before the end of this video. I'm sorry. So x equals 3 is that line of symmetry. Now we're looking at B, and we're saying, can you draw a vertical line straight up and down so that he maps onto himself? Well, you might think like, okay, let's try and draw this line, like the y-axis. But if I map this one over here, he's going to go this direction. And if I map this one over here, he's going to go this direction. It's going to make like an X pattern, okay? So he's not going to be exactly perfect, so this is not going to have a line of symmetry. No line symmetry. Okay, no line symmetry. Okay, let's go to the back side and then talk about point symmetry. So the graph of a function has point symmetry if it can be rotated 180 degrees about a point so that its rotation maps exactly on top of itself, okay? 100 degrees is like a half of a circle, so it's just like taking your paper and flipping it upside down, okay? So state whether the graph of each function has point symmetry. If so, identify the point, okay? So we're looking at this thing. And what I want to do is I want to take this and I'm going to flip this upside down. So this part's going to come down here and this part's going to come up here, okay? You guys, if I did this in class, it'd be easy to see because I just take the paper and I'd flip it upside down. So take your paper and flip it upside down for me really fast while you're watching this video. Your paper, and if you flip your paper upside down, you should end up with something that looks like this, right? If you flip it completely upside down, it should look like that, which is exactly the same as what it was before, right? So this one does, in fact, yes, have point symmetry. And the point that we're rotating him around is this middle point right here where he's kind of flipped around. And that looks like it's centered at 0, 0. So 0, 0 would be my point of symmetry. Okay, so it's just kind of like wherever that middle point is at. If this thing was set to the side a little bit and we were doing like here, this would be my point of symmetry, okay? It doesn't have to be 0, 0. It's whatever that middle point of your graph is. I hope that made sense a little bit, okay? Part B says, can we flip him upside down and him look exactly the same as what he was before, okay? If we flip him upside down, he's going to look something like, he's going to be over in this corner actually. He's going to look something like this, right? If we flip him upside down. So if you do that to your paper and you flip him upside down, he will look something like that, okay? Which means he is flipped. Here he's facing down. Here he's facing up. So that is not giving me exactly the same figure. So no rotational symmetry. Or point symmetry, I guess you could say. So no rotational symmetry or no point symmetry. Now, going off of line symmetry, he does in fact have a line of symmetry. So let's do that. That line symmetry is a vertical line going straight up and down. Here's where the y-axis is. So that would be a line of symmetry at x equals 1. So he does have line symmetry, but no rotational symmetry. A, does he have any line symmetry if we draw a line straight down the middle? This would have to be on this side, so we'd have to go like this, and this would have to be on this side, so he's not going to have line symmetry. He does have rotational symmetry, like we said, but he does not have any line symmetry. Okay? All right, so hopefully you can identify those. I think in your homework assignment, it gives you some actual pictures maybe to do. I don't remember. But use the rest of your time to work on that page 100, all right? We'll turn both this one and 2-1 in tomorrow after we go over questions, okay?